Hello everyone. Today is the last lecture, which is for 12th week for this course, Computational Physics, under Nptel banner, and I am Sipan Mandal as an instructor, uh, and I am working at IIT BHU as a Prime Minister Research Fellow, and to conduct this type of live sessions for past 12 weeks is one of my deliverables towards PMRF scheme. As I said, that this is the last class for this live sessions, and throughout the course we have learned about different from standard Fortran program, how to write them, and as the course progresses, the difficulty of the courses in terms of the length of the course, as well as also we learned about different science goals like Ising model and then molecular dynamics, and also in between we learned about how the trapezoidal Simpson rules, as well as the partial differential equation, ordinary differential equation solutions. So we learned a lot throughout the course, and I tried my best. Obviously, in most of the classes I have to just deliver the lecture by myself only, because no one was there uh, for attending those lectures live. So I don't have that opportunity to interact with students throughout the courses. And today also, as usual, no one is there. This is already 5/7. As per usual practice, I am just starting to deliver the lecture, and hopefully it will reach all the peoples, or all students who will require it to submit their assignments. And in the last class we learned that how to write a molecular dynamics code, but at that time I wrote it in a manner that it is not that well structured. So in today's lecture I will again show that, because the questions what we have in the 12th week will need that code again, and it's better to understand that in a better manner. So I'm going to do that. And also in this week's lecture there are 2-3 more questions, uh, but unfortunately due to some illness I could not prepare them for all the questions fully. Instead of that, I wrote a little bit some subroutines which you can use for solving those questions also. So I will share those slides also, so you can write your codes. I mean, you have to just modify the codes a little bit, not very much, and you can got those answers. So okay, let's move on to the question. So here is the question. I hope it is visible. Okay, let's make it slideshow. So do a molecular dynamics simulation with 1200, that means 1001 particles, in 20 into 20 into 20 box. You see, initially we have considered that okay, sigma to be 1. So every one of the lengths considered in the simulation will be in the unit of sigma, where sigma is taken to be 1. So sigma is basically the diameters of those Lennard-Jones particles. So basically the particles under the Lennard-Jones potential. Okay, and at this time the dt is taken to be 0.0025. And what is the difference between that code which I discussed at the earlier class, at the last class, is there we don't consider some neighbor list. That means if we consider the interaction from one particle to all the particles, so that will take much time for our simulation to run, because then let's say you have 12 1200 particles. That means for a particle it will it will calculate the interaction forces and potential from the interaction from the other particles except that one particle. So it will take much longer time. But instead of that, if we take a certain extent up to which we are considering that okay, all the particles up to that extent is considered as neighbor for that particle, and likewise we just consider those interaction up to that extent, then our neighbor list will help us in such a way that the simulation will run in less time. Okay, so that is the motive of use a neighbor list. So how to use that, you can find the details from the lectures given by the faculties. Also I will discuss a little bit later on. So what happens is we have to take just a second. Yeah, so we have this, and yeah, so basically what happens is, let's say you have particles like this, okay, and if it is the simulation box throughout, okay, let's say this is your simulation box and there might be more particles than what I have drawn. So let's say you have this particle, okay, so for this particle earlier what we are doing, we are calculating the interaction from this particle also, but it might be happen that okay, this particle will move, each one of the particles will move, but it will not come closer to that much closer such that we need to consider that interaction as well, but we are considering it earlier. So what we are doing, that let's say you have a cutoff upon which the potential is going to cut off, so we have taken an extent, the length extent up to which we are going to consider the neighbors. So let's say if this is your RC, then we are going to take another annulus for a bigger radius, which will be of the radius of RS, okay, and that RS is the extent up to which we are taking the particles within that as the neighbors for this particle. Okay, so this is what we have doing. So this is the change which we have to implement, and then after the first 50k, it is 50,000 iterations are over. Why do we need to wait for that? So that's because if you see the lectures and as well as the previous live session, you see up to a certain extension, just a second, up to a certain extension, what will happen, that there might be some oscillations in kinetic energy or potential energy on the total energy. So we have to wait for that time or that moment up to beyond which the total energy and the other energies will remain constant. That means that will reach a equilibrium such that after that we can calculate or we can collect the data for calculating some thermodynamical quantity such as the PR correlation function. Okay, so what happens in this question, that after the first 50k iterations are over, start collecting data over the next 2,50,000 iterations to calculate GR, which is the PR correlation function. Okay, so the bean size of the calculating GR is 0.1 sigma. So data to calculate GR is collected every 100 iteration. So you have to calculate GR, okay, and the data to calculate the GR has to be collected every 100 iteration, not at each iteration, okay. So initial configuration of particles in the can be random, or arrange the particles in a lattice such that box is uniformly filled. There are no large voids in the box. So what I did is I have taken to be them to be random, and I have to make sure that there will be no overlapping. Since I am making them random, then I have to check for the distances between them. If the distance is greater than sigma, that is the diameter of the particles, then only I will take that choice. Otherwise I will neglect that choice or ignore that choice. Okay, so that is the essence of the initialization of the particles in terms of their position. Okay, so our first question is, in the first 20,000 to 30,000 iteration, the most number of neighbors, so that means within the distance rs that a particle could have, lies in the range. So you can write your code in your way. Okay, so I tried in my way, and I think it will subjected to some modification if you try to write it. Okay, so I will just depict how I wrote it, and it will be much more structured than the code which I provide earlier, because right now I have some subroutines and I call them within the main program. Okay, and all of the subroutines are well defined in today's lecture. So just a second, I will I will show, or I will discuss about the code. So yeah, so you see what I've done. So initially, as before, I have a module in which I have defined all the variables, almost all the variables which will be used in the simulation. So this JZZ, these are some high positive numbers which will be positive or negative numbers which will be used while doing the randomization. Okay, and as per the question LX LY is that both of each of them will be equated to be 20, and the number of particle in this question is 1200. KBT is for simplification to be taken as 1, and that to ni is the total number of iteration, and that is 3 lakh. Mass is equals to 1 for simplification. Ni underscore equal, that means up to which we are given the simulation, we give the time to simulation to reach an equilibrium, that is 50,000. Okay, so RC, at which the potential will cut off, is as per question 2. RS is 2 plus 2.5, so that means RS that can be taken to be 4.5, and sigma is 1, and then sigma 6, sigma 12, these are some definition, because we don't need want to write again and again in each of the subroutine these terms, that then we have to make this module, and I have to call module in each of the subroutine. So we don't need to write it again and again whenever we are writing the subroutine. We just need to use this module again and again. Okay, so that will I mean, if it is we have to write it again and again, that will be cumbersome, so we don't follow that step. So what happens is, you see, if you look at the Lennard-Jones potential and the force, so what it does is at the distance of RC, the total potential as well as the force has to goes to 0, and that condition imposed some different relation between the exact force which the Lennard-Jones potential provides. Okay, so to do those we need this parameters also. Okay, so after that we have defined the arrays which we need to store the values of the position, velocity, force, acceleration at each of the for each of the particles, for each of the component of the particles, and at each iteration. Okay, so so if we look at the main program here, so what we look is so we use the simulation para, that module, and we are as usual used implicit none, and those variables which are not defined in simpera, I have defined them in this program. Okay, only those. And then what happens, I have called two subroutines which will be used to initialization the position as well as the velocity. Okay, so after the initialization of position and initialization velocity, so what we have is the velocity array and position array for those 1 2 0 0 particles. That means you have 3600 values of position as well as velocity. Okay, so after that, what we are going to do, we are going to calculate the forces, and that force again is going to update the velocity. Okay, since the full force will give us some acceleration, then the velocity will change, and then that updated velocity will then going to update the position as well as again at the next iteration it will update everything. Okay, so initially what I have done, that initially I have initialize the position and velocity, and then we have a calc force subroutine which will calculate some new forces. So initially there is no force, but with this position and velocity initialization we are going to calculate some force, and so we have now the initial position, velocity, and the initial force. Okay, after that what we do, we just write, or we just take two loops. In first we take the simulation time to be 1 to 50,000. In that case, why we need this, we need to check for the equilibrium. So for this 50,000, what will happen, it will essentially reach the equilibrium. Okay, so basically the potential energy, kinetic energy, and the total energy will reach the constant value. It will not oscillate. Okay, and even if it is oscillating, then that oscillation is very small to be considered as a oscillation. Okay, so again we will update here the position, and then we will see that okay, that force I will come to this, and then I will calculate the force again, and then velocity will be updated. So after that we can write it in this way, that for ith particle, for a particular particle at some number of iteration, what will be the number of neighbors for that particular particle. Okay, in this way you can print the number of neighbors for a certain particle at different number of iterations, how this is going to change, and that will give you the answer for the first question. Okay, so that's the thing. And after that what I have done is okay, so first thing is we need to understand the subroutines which we have already called. So let's take a look after in a sequential manner. So initially you need to initialization the position in INIT and velocity INIT. So to initialize the position INIT, you see that again we have used the use simpera, right? So the module is called, and again some variables are defined because they are not in the simpera. Okay, so then position of the first particle. So here you see the position 1, position 2, position 3 is the three components of the position vector for the first particle. Okay, and they are given as the randomizations, random numbers. Okay, so these will be within 0 to 20. Since deep float LX will give you 20 and ran 1, this will give you uniform random numbers within 0 and 1, so it will essentially give you 0 to 20. And similarly for the y and z component. Okay, so we have initialized one particle's position. Now what we have to do, we have to check for non-overlapping condition, and so for that we have again a do loop. We have initialized all the particles, and then what I have done, that for j equals to 1 to I minus 1, but we calculate the distance in each of the component, and then we see that if it is greater than sigma, only then we are going to take this choice, otherwise we are not going to take this choice. So you see here, this is basically the periodic boundary condition. That means that you have some let's say we have two particles which are much closer, then we are going to calculate that position, the difference between them in that way. But if it is very far away, so for example at two different extended at different extents, that means it will consider that mirror image point, and that has been calculated here. Okay, so after that those r1, r2, r3 are updated fully, and then we are going to calculate the distance between them, and we say that if distance is less than sigma, that means it will overlap. So in that case we are not going to take that choice. We are again going back to that randomization, and again we are doing the same thing. Okay, so if it is greater than sigma, then we are going to update, we are going to take those values. Okay, fine. So that those can be written at a file. Okay, so after that we also use the velocity init, which will give you the velocity in between minus 0.5 to plus 0.5. Again we have used the randomization. Here we have the velocity constant, which will be coming if you calculate it analytically. So after that what actually we have done is this average velocities and these things. So we take care of the total momentum initially to be 0 in the in this simulation box. Okay, so that has been taken care for by those average velocity, and use of those average velocity to update the velocity array. Okay, so initially the total momentum within the box will be 0, and the velocity initialization and position initialization is done. Okay, and this random this function is used to randomize our position and velocity. Fine. After that, this we have to calculate the force, right? So so force has been calculated here. So what has done is, again we use the simulation module simpara, and again all those variables which are not defined in this, we have defined them, and then we take that, okay, force and PE, these two are taken to be 0 initially, and then what I have done is we call the neighbor list, because this time we tried the simulation for a larger time. Then at each time step we don't want to calculate all of the interaction for all of the particles. Instead we try to calculate the interaction between those particles which are within the RS distance which we have defined beforehand. Okay, so how this neighbor list has to be written, that I will give you the example. Okay, so what I have done is, for a particle we have this x1, y1, z1, those are the x, y, z component of the position, and then for j I plus 1, so there you see you have those x2, y2, z2, and this p Okay, this P has been calculated from the neighbor list subroutine. This is not the similar to that before, that has been done before. Okay, so after that you have this x, y, z, so which are the difference between the x, y, z coordinate of the two particles, and if it is greater than lx2, then we have to calculate the x in this way. These are the those mirror image problems. Okay, so after that we can have the r equals to square root of this. Okay, and if r is less than equals to rc, that means if r, the total distance between those two particles, is less than the potential cutoff, only then we are going to calculate the forces. And you see, these things can be find out from the lecture, that the potential will have this kind of a form, that 4 epsilon sigma by r to the power 12 minus sigma by r to the power 6 minus ufc plus fc into r, where ufc has been defined at the beginning. Okay, so again we are going to update the potential energy array. Okay, which will be given to be, so this might be here, this will be n. And so LJF1 is this, LJF2 is this, so this is the force term and this is the potential energy term. Okay, so this way the force has to be updated, and you see that here, so we have two particles, right? So they will have some action and reaction. So if our particle will be subjected to some force which is some plus sign, then the other particle will have the minus sign, because those are oppositely directed, right? So you see here, for ith particle, all of the three components will be updated by some plus sign here, but for jth particle, all of the three components will be updated by minus sign. Okay, and this x by r, y by r, z by r are given to be to find out the x, y, z component from this vectorial representation of force. Okay, so this way the force has to be calculated. Now if we look for the neighbor list, so here comes the neighbor list. So you see, you have again use those module, and then define those variables which are not defined. Okay, so again we have two arrays, one is n underscore nay and n underscore list. Okay, so after that what I have done, again as we done for force, this time we have to check that if r, which is less than rs, okay, the distance between two particles, if that is less than rs, right, up to which we are going to consider all the particles within that to be neighbors for that particle. So if r is less than rs, only then I am going to update this. So this array will give you the total number of neighbors within that for a particular particle, and this array will give you that number of particles. So not the number of particle, jth particle will be the ith neighbor of that ith particle. Okay, so that is the two arrays here. Okay, so this neighbor list will be used in the calc force subroutine to calculate the interaction between the particles. Okay, also if we remember last class, there has been another subroutine or another thing which have been discussed about thermostat. So what is the reason to use a thermostat? So basically if we don't use thermostat, that means the temperature corresponding to or associated to the system will not remain stationary. It will change as the simulation will progress. But if we use the thermostat, that means we are going to make the temperature to be constant, that means the kinetic energy will remain constant, and therefore the potential energy and the total energy is bound to change, but kinetic energy will be remaining constant. So these subroutines will be called in the main program at different stages of the simulation, as the science as well as the question will ask for. Okay, so we have discussed about neighbour list, we have discussed about thermostat, we have discussed about calculation of force, and now we have to discuss about the update of velocity, how to update the velocity, right? So initially we have the kinetic energy set to be 0, average of Vx, Vy, Vz set to be 0, and then this is the way we update the velocity array, where we need the force components at the present simulation, present iteration, as well as the force components at earlier iteration. Okay, so in this way the velocity arrays will be updated, and these are added to the total average velocities, and kinetic energy can be written or updated in this way, because m has been taken to be 1. So we have to just calculate the v square. So this is vx square, vy square, vz square. Okay, so basically vx square plus vy square plus vz square will be ending upon v square, and here you see half deep float mass, which will be 1 into v square. So this will give you the kinetic energy. So when we are going to calculate the potential energy, that is within the force subroutine, and here while we are updating the velocity, we also update the kinetic energy here. Okay, so we have the position initialization, velocity initialization, and then we have the force initialization through the force subroutine, and then we start the simulation, and we wait for 50,000 iteration to the system reach for system reaching the equilibrium in terms of the energy values. Okay, after that we are going to calculate, or we are going to collect the data for calculating the thermodynamical quantities such as pair correlation function. So till now we have those three things, and now if we go back to another thing we have to understand is the how to update the position. So if you look at these things, you find that that formula which we studied, maybe I studied it maybe 7 to more year ago, that is the position is equals to ut plus half at square, that is basically given here. Okay, so that has been used to update the position, and see here the force has been used and velocity array has been used also. So, and after that this thing is taken care of the periodic boundary condition. Okay, so all of the subroutines are almost understandable right now. So I think you can write your own code in your own language, because it is already 12 classes, and you have written the codes in the near past. So I mean, you might be have some capability right now to write your own codes for other different problems. Okay, so last thing what I am going to discuss is about a subroutine which will be calculation of thermodynamics. I unfortunately I don't I am not able to write because of some illness all the things as the assignment is subjected to, but I think this is enough discussion about different subroutines which will help you to write the other things of the course, right? So that means what will happen is there is a sorry yeah so you have the Scalp Thermodynamics subroutine, and I am going to depict how it is. Okay, so you have this subroutine here, and as before we call the module, so we have all the variables which are defined within the module, and we have to define some other variables which are not defined in that. So after that we have some arrays, right? So what will happen is basically I have to give some example here. So just a second. Yeah, so let's say you have some particle here. Okay, so you have this box with this sphere within that. So what will happen, what are the particles within this sphere? Those are at certain distance, right, from this particle. So this will give us some density of the number density of particles within that particular annulus, and if we have a larger annulus, then it will calculate for this to this distance what are the number of particles. Okay, so this way we are going to bin the total box, not the total box. It will take the half of the length of the box, and at each of the distance with a variation of 0.1, right? So let's say we have some particles from 0 to 0.1. So after that it will be 0.1 to 0.2. So in this way we have some bins for the distance between two particles. So in this bin there will be some particle, is in this bin there will be some particle, right? In this way we have to take all the bins, that means all of the bins which are different in terms of the distance between two particles, right? So this will be a bin, this will be a bin, this will be a bin, and so on. So okay, so after that what will happen, that within this bin we have a some number of particle for a particular particle that will be give the neighbors within that much distance from particular particle. Okay, so after that we are going to change that particle for which we are calculating the number of neighbors. So for each one of the particle we are going to calculate the neighbors at certain distances, for example 0 to 0.1, 0.1 to 0.2, 0.3 to 0.3, as so on. Okay, for each of the one of the particle we will going to calculate this number of nearest particles. So after that what will happen, for each one of the bin we are going to calculate the average number, okay, average over the total number of particles, average of the nearest neighbors or number of particles within that particular volume or within that particular distance, and we have to average over those particles. And also after averaging over those particles we have to average them over the total number of iteration. So for a particular iteration you have to calculate the number of particles for a particular particle. Okay, so what we have to do, we have to start from a particular one particle. For that we have to calculate the total number of particles within each of one of the annulus. For example 0 to 0.1 you have 5, 0.1 to 0.2 you have 6, 0.2 to 0.3 you have 7. Okay, and so on. Now we have to go to another particle and again calculate those number of particles for those bins size. Okay, so for example for particle 2 you have you have 4 particles within 0 to 0.1, you have 5 particles from 0.1 to 0.2, and so on, and successively you have to take this calculation for 1200, that means 1200 particles. And after that, in each of one of the bin, you have to sum over all the particles, all the number of the particles within that, and then you have to divide that by total number of particles to get the average of over the particles. Okay, so now you have the average for a particular iteration, and after that what it will happen, that for each iteration you are going to calculate the number of averaged the number of particles averaged over the particle. Okay, so and then you have to average over those iterations, the total number of iteration for each one of the beam. And then if we plot the averaged number of particles with this beam sizes, this, let's say for 0 to 0.1 you have 50 particles, 0.1 to 0.2 you have 55 particles, and this way you will get a plot, and that will have some peak that will tell you that okay, so throughout the simulation box at that much distance there will be much peering, there will be much that will be the best possible difference between the particles, so that will give you the peer correlation function. Okay, so I think the algorithm is clear. Okay, so you see here I have the Scalp Dynamics thing. So here do k equals to 1 to n bin, and then what I have done is I have taken left and right extent of each bin, and I have said that here that if r is greater than this left segment and r is less than the right segment, then I am going to take that particle under consideration, and I have stored all the numbers of particles in this way. So this will sum up, right? And after that I have just divided by np. One thing I want to point out that you have to divide this number k by 4 pi r squared dr. Okay, so which I have not done here by some mistake. So you have to divide this thing by 4 pi r square dr. This will be the better thing to do. Okay, so these will serve you the average over the particles, but not serve you the average over the iteration. That part you have to do, and I hope you will be able to do that, because this is already 12 classes and you are already writing your codes by your own. I am just for help throughout this session. Okay, so so one thing just point out that for 20,000 to 30,000 what you see in this main program. So I have written these things in the terminal as the code was progressing, right? So that will be around this. So you see this is around 80 to 90. So if we look at this answer, so I this will be the correct answer, 80 to 100. Okay. Okay, so this will be correct answer. So I hope now you can write your codes to solve the other questions. For example, in this question they are asking for the position of the second peak of pair correlation function G is. So for this you have to write a little bit much more code, which I have to provide in this lecture. So in this you have to check for the plot between gr and r. From there you have to find out the peak and corresponding value of r for that peak. Okay, from that you can answer the question. So thank you very much for not attending, I mean. So I hope it will found you through YouTube, and So this is the last class. I am not going to take, or I don't have to take any more classes for this course. So thank you very much everyone. Yeah, so I will stop here.